So, good afternoon, everybody. It's a pleasure to be talking at this workshop. Uh, Today, I decided to talk a little bit about a, a lot of things, but I will try to be very informal in the sense that I will not focus in any of the equations. I will describe more or less how things are computed, but rather than in the why it is important to study these things. And for the topic that I decided to speak, I will talk about bosonic fields, compact objects, and binaries, and how these things mix together in some scenarios, and also about some of the works that I've been doing with some of my collaborators. So I divided my presentation in the following way. I will give a very short introduction that possibly will be a bit boring for a lot of you, but it's just to play in the field. Then I will discuss the self-gravitating fields, in particular bosonic fields, describe how black holes interact with these fields and what consequences we can extract with these interactions. And lastly, I will mention a little bit about this work that this couple of works that I did this year about binary swimming in the fields. In the case that I will discuss is not in the fields, is in the matter, but I will discuss how we expect that we would have a similar results if you have a field profile and binaries evolving within it. Okay. So short introductions. So basically, to start, we have to consider what is gravity, right? The understanding that we know about gravity today is due to Albert Einstein. Basically, he put this equation describing how the gravitational fields works. It is a tensor field, and then you have the matter that also obeys the equations. This comes from an action. In this case, I'm also putting the cosmological constant here, but in this presentation, I will not consider it. And in the end, from all the experiment that we have so far, we know that basically gravity should be described as a geometric quantity. I mean, all things that we have experiment point in this direction. And you can see this very nicely written in Will reviews about testing gravity. So this is consolidated with the words by John Wheeler. Usually, I mean, attributed to him, that space-time curve tells matter how to move, matter tells space-time how to curve. Okay, and another thing that is a consequence of GR, you may think in that way because it goes from it follows from the Einstein's equation. Is that of black holes. The first solution that described a black hole was obtained shortly after GR. Essentially, this can be thought one of the way to form these black holes is from a gravitational collapse. So basically, you have an initial star which is beyond the critical mass, and then it collapses to a black hole with a different mass because you have mass ejection and so on. And for a long time, this was thought as an exotic object, but now we know that they should exist because all the observational features that we have out there. And another important work in this direction is that the one by Roy Kerr that described the rotating black hole. That is a very nice historical perspective of the finding in this paper by Visser. And essentially, rotating stars are a lot more complicated because they are characterized by many more numbers, representing essentially the higher multiples of the star. But in the end, quite surprisingly, in GR, we have that the star, if it collapses to a black hole, can be described by just two numbers, which is the mass and the rotation of the star, of the black hole. Sorry, this essentially is the Noether theorem. So note here that I'm not considering electrical charge because we expect that also physical black holes to be uncharged due to many mechanisms. Now we have these massive detections of black holes from the library vehicle collaborations. And what essentially this is telling us is that black holes are out there, they form binaries, and we can detect them with gravitational wave, and we can try to find new physics with it, because now we have a lot of detections, and we can start to playing with different phenomenology involving black hole binaries. So about the characterization of black holes, we have, as I told you, that rotating black holes are just characterized by these two numbers, right? This led Chandrasekhar to say that they would be the most perfect objects of nature, because they are purely space-time and they are very simple. So sorry. And also this led John Wheeler to say, at least what people usually say, that black holes have no hair. But there is this video about it that Wheeler said actually that Bekenstein said it. And he also mentioned that in the conversation, Feynman was present and saying that this was a very obscene thing to say. And then this led to all these no-hair theorems and uniqueness theorems of black holes in GR, right? And then you might think that black holes are boring because, okay, you have just two numbers, but then you have a lot of things going on around black holes, right? You have, for instance, just to mention one, this is one symbol of an online seminar project that a colleague of mine is doing. He used this photo of the Event Horizon collaboration, right? Which now we have the movie, which is kind of say movie, I mean, in some frames. And then you note that there are a lot of dynamics surrounding black holes. And we can try to add things to these dynamics. And in this presentation, I will try to add some simple things. I will not consider matter with magnetic fields and you know, higher temperature. Just what would be the simple things that I can add to space-time and try to see how GR acts with it. So basically, I will try to add this bosonic field. Here I'm showing the GR action, essentially, the Einstein-Hilbert action, with a Procca field. So you have the mass term here. We have a scalar field, a complex scalar field. And you might have also an interaction between the complex scalar and the vector field, right? The matter here usually is described by some perfect fluid, right? Okay, so you might ask from where these fields come from, or where the fields come from, and there are a lot of answers to that in the literature, but I will not focus on these answers. I mean, Carolina already spoke about what we don't know about the universe. There are a lot of mystery, and some of this part might be light scalars and light vector fields. There is the axion that can also be described by these types of fields. Okay, but I will not focus on the details, but of the origins of this field, but rather in the phenomenology that we can describe with it. The first thing of my after the introduction is about self-gravitating fields. Okay, because we know that everything gravitates. So if you let a field in your empty space-time, it will gravitate with itself and then try to interact and collapse or disperse or etc. And in this scenario, what we find is boson stars. So Fabrizio already spoke about boson stars. Also, Francisco today talked about these geons from Wheeler, which essentially are the precursor of boson stars. And the simplest case of boson stars is just described by a complex scalar field with a master, right? And with this, you can describe this mini boson star. So essentially, these two first rows of this plot are the metric function compared with the black hole. The black hole is this dotted line, and what you have here is that the metric is very similar to the black hole one. If you imagine that 6m is the less stable circular orbit in Schwarzschild space-time, and then you have that outside of it, you can describe very well the space-time by a mini boson star and the black hole. They will be very, very similar. These are two different kinds of boson star, right? And this is the profile of the scalar field. You obtain this by solving Einstein field equation with just a complex scalar field. This is, I mean, one of the simplest cases that you can imagine, that you can add matter and then solve the equations, right? You can also describe all the types of stars, for instance, with self-interaction. This is with the lambda 5/4 term. The net results in this case is that the compactness would be the radius of over the mass. It decrease. I mean, the compactness increase. Sorry, the mass over radius. The mass of a radius decrease, and then which means essentially that your star is more and more compact, more and more similar to the Schwarzschild case. And this is a solitonic case, which is a particularly interesting type of boson star, because it exists even if you turn off gravity. In which sense it exists, the solitonic configuration exists even if you are just at Minkowski space-time and try to solve your equations. And this type of stars, this solitonic one, can be very, very compact, right? So you also have more similar, more axion-inspired stars. So this is the axion stars with, so this is not 2015. This was supposed to be last year. Sorry about that. This was a work done in collaboration with David Guerra, myself, and Paulo Pani, in which we consider a potential that is more, I mean, more inspired in the action from the Axiverse. And then what we have is that you can have, depending on this decaying term here of the axion, you can have many stable phases of these boson stars, and they can be very, very compact. Here I marked here is the mass ratio curve, and here I marked the UCO limit, which would be essentially a star that is compact enough such that it presents light rings surrounding. Light rings is essentially circular null geodesic orbit. Okay, so you might think that apparently this region is not crossed. This UCO region is not crossed, but you have to remember that these stars, because the field decays exponentially, they do not have a proper radius. So you have to truncate at some point, and then you describe this effective radius. But this star can have light rings, but they are not as compact as a black hole. I should mention that. I will go back to that later. And you also can have these structures formed by just real fields. I mean, you might imagine, okay, but that would be complex. What about real fields? In real fields, what you have is that you have some kind of solitone structures, but the problem is because the metric fluctuates, I mean, the metric oscillates, you have that the solution essentially is leaking through the emission of the waves. So your solution is, in the end, unstable. But the thing is that this instability should be viewed with care, because the time scale for the instability is very, very long. So in effective terms, you can have a lot of things going on surrounding the star, and for all that matters, it is stable, right? So this was coined as oscillatons. The word discovered by Macedo and Swan. And you have both boson described by scalar and vector oscillatons with different mass radius curves. This is a comparison between the boson star curve with the oscillaton curve, okay? And regarding gravitational wave emission by binaries formed by boson stars and other objects, you can have some interesting signatures when you are dealing with extreme mass situation spires. So imagine that instead of having a supermassive black hole, you have a supermassive boson star at the center of the galaxy or whatever. And then you take a small black hole and put it to orbit around this boson star. So you have that the overall emission is essentially the same of that of the black hole, because in the end, what you have is that the space-time is very similar to the black hole, and if you are in an orbit far away from the star, what you have is that the emission is essentially the quadrupole emission. But the thing is that the boson star, boson stars have a mode structure. I mean, the quasi-normal modes of these boson stars, they are very different from the black hole case, and they can put signatures in this spiral emission. Here, I put the gravitational flux to infinity from these orbital boson stars. This dotted line is essentially what you expect from the quadrupole approximation. And in here, you can see some peaks, and these peaks are due to resonance happening between the wave emitted by the orbiting object and the mode structure of your boson star. So you have these peaks that can have magnitudes of order bigger than the similar quadrupolar thing that I discussed to you. This happened for either the mini boson star and also with models with self-interaction. And then the fact that this has in the gravitational wave emission is essentially the one to introduce some phase in a quicker change of phase every time the orbit passes in one of these resonant configurations. So I thought that this boson star can be very different in the spiral scenario, but also in the ring down scenario they can be different, because after all they are stars, and these stars have a mode structure very different from that of black hole. Here you can see the real and imaginary part of the mode, and this is also represented by the collision of two boson star here, depending on the initial setup that you have, the initial data that you have, you can end up with a star, which is in this case, and the mode's very, very different from that of the black hole, or you can end up with a black hole in which the ring down is more similar to a black hole. So this is just to play around. It's just a simulation of a collision of boson stars in which you end with a boson star. This is for the solitonic configuration, the one that can exist without gravity. And one interesting collision that happens in this case, which in the end we did not put in the paper, but I will show because it's funny, is that depending on how you adjust your initial data, you can have something like this happening. So this is Einstein's equations with a scalar field that interacts a lot. I mean, the self-interaction can make this star very, very compact. So you have this, let me show again, this kick one another, like two balls bouncing each other. But also notice if the star is compact enough, the ring down can be very similar to that of the black holes. We illustrated these boson stars are not that compact because at least the models that we have up to now cannot describe, I mean, a clean ring down in the same sense of gravastars, for instance, in other kind of models. But here we show that different models also have the same ring down. This was a couple of years ago. And if you could have a boson star, for instance, that's compact as this object that I'm showing here, you would have the same thing. So when you have a compact object that is very, very compact, we should take care when saying that the ring now can be clear, seeing that this is not an object, a black hole. And also another thing that happens when you consider this orbiting, this spiral of objects around boson star is this dynamical friction and accretion. So essentially, dynamical friction, if you imagine a uniform medium and you put an object to orbit, just interacting gravitationally with this medium, what would happen is that it would accumulate some density behind it, which is the wake, and this accumulation of density would generate a force, a net force, that would act as a friction term in your object, in your orbiting object, right? This is a hydrodynamical simulation made by King with their object in circular orbits, and we try to implement that to see what would be the effects of an orbiting particle around the boson stars. And depending, of course, this also depends a lot on the parameter that you use to describe this object. This is an example of an orbit. Because of the accretion, the mass increases, but depending on the sound speed and how you model the drag, you can end up with different things. You can end up with an orbiting case in which the particle quickly evolves to the center of the star, or one that takes very long time, but do present some signatures in the wave amplitude. This is essentially the wave amplitude for different cases. And you see that depending on the parameters that you describe, this gravitational accretion and drag, which are what I call dissipative force, you have a different scenario. Another thing that is interesting is because these boson stars, they have some of the solutions that you can generate with a scalar field in Nast's equation, they are unstable. I mean, essentially the solution that present nodes, which are this one, I describe it here. If you perturb it, it will emit scalar waves and you will go to the ground state with our nodeless solution. But there was work by Giovanni et al. This year that showed that if you put a star in the center, a neutron star, for instance, or the object in the center, you can stabilize this this kind of solution. This is very interesting, at least to me, because essentially what you're saying is that a star at the center is able to quench the instability of these bosonic cores, right? So, and talking about instability, we'll just quickly pass through it to remember you all that rotating boson stars do exist, but they are unstable. At least the case that you have, the simplest case, that is essentially when you have the mass term only. As I mentioned in Fabrizio's talk, if you put self-interaction, the scenario can change. So I put some questions here just to guide discussions. That, I mean, there are things that I really don't know, but it can be I can be naive. I mean, they might have a simple answer. The first is rotating boson stars are unstable. What to do? I mean, should we stop studying them, or, for instance, could something else stabilize these solutions, like the neutron star at the center of a boson star stabilize the excited solution of these boson stars? I know that the instabilities are different, I mean, from nature, but it's interesting to see this kind of thing happens. Another thing is that whether we can stabilize these solutions with other things than self-interactions. For instance, in the action case, it interacts with usually with vector fields. So if you put an interaction between the scalar and the vector field, with the vector being massless, could this additional, let us call dissipation through radiation, quench the instability of this boson star, these rotating boson stars? What about rotating oscillatons? These are things that are much less studied. And would be interesting to see what if the time scale of the instability are the same of the boson star, or if they are unstable at all. Another thing that it has not been studied yet is that if the extreme mass ratio inspired in the proxy star case are the same, as in more or less the same as in the boson star case, in the scalar case, and how compact can we go? I mean, I showed you that some potential can generate a very compact star, but these stars are not as close as the horizon as we wish to mimic black holes. So it would be interesting to check if there is some natural limit, because as I mentioned in the formation of wormholes, I don't remember I mentioned, but I will say it out loud. If I didn't mention, I thought about it, but it didn't go through. Because in the formation of these very, very compact objects, what we have is that you can describe a Galois star, for instance. It is a solution of your field equation, but the formation of these objects are more complicated to do. Boson stars is a thing that we know how to form. We can solve the equations and show them forming dynamically. So it would be interesting to see if we can, with just bosonic fields, form a star that is arbitrarily compact. All right. So part 3 is black holes and the fields. We pass very quickly to this one. So essentially, this is the anatomy of black hole. Sorry, there is a Portuguese written here. If you think about a black hole, you have outer ergosphere, inner ergosphere, and the event horizon. Black holes present a very interesting phenomenon, which is the Penrose process. Here, this Penrose image, he won the Nobel Prize this year. So you have a particle that enters the ergosphere, split in two, and one is swallowed by the black hole, and the other goes away. So depending on the energy, because you have that the energy inside the ergosphere is negative, you have by energy conservation that this particle that leaves is more energetic than the one that enters, and you can extract energy from the black hole. We all know that. So, but what is the relation with the bosonic fields? So, yeah, in bosonic fields present this superradiance, which essentially, when you send a wave with a certain characteristic to a black hole, it interacts, and it can reflect a wave with a bigger amplitude than the one that entered. So, as I mentioned to you, this wave has to have some relation with the rotation of the black hole. And you can amplify, depending on your field, if it is scalar, electromagnetic, or gravitational, in different ways. So basically, gravitational radiations amplifies much more than the scalar and electromagnetic one. But if you put a mirror outside the black hole, what you get is that your wave can interact with the black hole being reflected, so with a bigger amplitude, reflecting the mirror, and interact again, being reflected. And then at some point, the mirror will not sustain the situation and it will explode. And you have what people call a black hole bomb, right? So we don't have mirror naturally, but I will speak about a way to form this mirror naturally. But usually you don't put a mirror artificially around your black hole. But you can kind of have the necessary gradient, but just put a mass term, because the mass term essentially it filters some frequencies that can escape the black hole. And if this frequency is within the superradiance condition, what you have is that you can reflect back and forth this wave, and then generate what we call the superradiance instability. So the superradiance instability can generate these clouds around the black hole. You basically go extracting mass from the black hole, and you have even a very ultralight field can have a conflict. I mean, can like face it a supermassive black hole. That's why you have this conflict between the ultralight and the supermassive. So the time scale for the instability is quite reasonable. I mean, so for a supermassive black hole, this goes for years. This is and even smaller from vector and tensor, but it can be observable in our lifetime. We generate a lot of signatures, like gravitational wave being sent from this process because the field amplifies and then falls back into the black hole and then send gravitational wave, but we're not mentioned here. I also mentioned that this can, like, there are other ways to generate these profiles of scalar around black holes. One of them is through these complex scalar fields that were described by Eugene by Heder and Hadul. Black holes with scalar hair. And another interesting thing that happens because of the mass of the field, I mean, when I'm not the mass of the field, because as I mentioned to you, don't put a mirror around black hole because it's impractical, but there are natural mirrors around them. One of them is the mass of the field, and the other one is the astrophysical plasma. So some of you might know astrophysical plasma, it filters some frequencies. I mean, you can try to describe the wave propagation in astrophysical plasma, and you'll see that the equation in some regimes can be described in a very similar way to the Proctor field equation. That is a vector field with a mass term, with the mass term being described by this frequency, which is the plasma frequency. All right. And one interesting thing that happens during the ring down of this kind of thing is that plasma might filter some frequency hiding the nature of the black hole. For instance, imagine that you have a charged black hole in the center of the galaxy or whatever. And then what you expect from the ring down of a charged black hole is that if the charge is small, the ring down is very clear because you only have the gravitational modes. But if the charge is high, from the collision of two black holes, the ring down will have this modulation. And these modulations come from the fact that you have two families of modes being excited. One is the gravitational mode, and the other is the electromagnetic mode. Because gravity couples with electromagnetic fields, you have signatures from both modes in both signals, in the electromagnetic signal and the gravitational signal. And what the plasma does, if it has a high enough and effective mass, so you see, I don't know if you can see, but this black curve here has this modulation, but the red curve in the ring down part has less modulation than the black one. The red curve would be the one with the higher mass. So the mass filters the electromagnetic mode from the signal. Okay. So just to discuss, I mean, as I mentioned to you about the instability of boson star, these hairy black holes were also found to be unstable. So I think the same question that we posed to the boson star hold here. I mean, what we could do to study this kind of thing, or should we throw away the sense that they are unstable and that's life. So evolution of plasmas in fields, I mean, the example that I showed you before is from a toy model. It would be very interesting to see if you consider additional physics to the plasmas, I mean, the effects of temperature and so on, how it modifies the whole scenario that in the whole discussion that I had with you here. The ring down of black holes with scalar hair. This is an interesting thing because, I mean, I would imagine that you, in addition to the modes of the black hole, you would have some modes related to the scalar head with the scalar profile. And if so, would we be able to see it in the ring down, or could you have like a scalar plasma or something that filters the frequency of the scalar mode? And also in spiral resonance, those resonance that we had from the scalar field, we also have from the case of from the boson star, we also have in the case of a hairy black hole, but it could be good to understand a little more. And finally, for the last part is binary swimming the field. This is from more recent works, and basically to show what a companion can do to the fields or to the hair of the black hole and so on. So the first thing is that if you have, imagine that you have an oscillaton. So oscillaton, the metric oscillates, as I told you. So if the metric oscillates, you would have, even in the Newtonian regime, a potential that is not precisely spherically symmetric. So you would have some additional profile here, which would be time dependent, and have this additional phi term here if your solution have some other symmetry than spherical, right? So essentially what you have is the central, the potential, the Newtonian potential, some correction due to the cloud, to the scalar field, and some additional correction due to the oscillation. And the interesting thing about this is that this effect can have drastic changes in some orbital configurations. For instance, you can have this beating pattern. If you start with a slightly circular orbit, you have that this circular orbit increases. This is the perturbation of that circular orbit. Increases and decreases in time, generate this beating. And this is because when you add this kind of potential, you generate some frequency that can resonate with the orbital frequency of the motion, and also I forgot the name, the orbital frequency and the frequency of the deviation of the radial motion. I've completely forgot the name, sorry. And very interesting, this kind of thing was studying the dynamic of galactic disks and also planets with disks like Saturn. And with these scenarios, you can generate this kind of orbit. This is in the co-rotating frame. You have this banana orbit. So basically, this is just the up part. You have also the bottom part, or otherwise would be a half of banana. But this is the banana orbit, and you have that you can do this. This is for the gravitational interaction. But if you also consider that your scalar field interacts with the matter, you have also like a moon orbit or something like that, which is a more a modification of the banana orbit. But this banana is more complete in the sense that it's bigger than the just gravitational interaction. And if you add the dissipation, what you have is that the orbit seems to converge to some point here, and this point here, the Lagrange point of your configuration. Okay. So another thing that you can have in this orbital motion is resonant configuration. I already mentioned this to you, but I didn't mention in this sense, because when you have this resonant configuration, you have some radius in which your object resonates with the cloud and the other compact object that they are orbiting, and this can lead to a depletion of the cloud. And this was described in this work very beautifully by Baumann, Shi, and Porto, in which they present these peaks, which are the amplitudes for this transition here. And at the time you have one of these peaks, you can deplete the cloud that is leaving, hovering the black hole here. They also put this very nice diagram, which essentially is the mass ratio, which is the ratio between the mass of the two objects and the mass of the field. So you can have regions in which the depletion is stronger and others that depletion is weaker. Each of these points is represented by this line here. So essentially you have this depletion. Think about this as being the cloud mass. And then you have that at some point you face a resonance, and this resonance make you deplete mass. So we extend that to other orbits, and very interestingly, because when you have eccentricity, because the orbital motion can be, because the source stem can be separated in other harmonics, you have much more frequencies to be excited than just this one. And this means essentially that you have many more possibilities to deplete your cloud, right? So you can have something like this. If you think about in the other work, was just a steep profile like this one with the zero eccentricity. But when you add a section, even a small eccentricity, you can drastically change the way that the cloud is depleted. And if you investigate this type of the resonance, you see that they are in the Lisa band. I mean, you could observe then if you have some of these kind of objects out there. And finally, the last thing that I want to speak is when you put into account not symmetric binaries, but binaries with similar masses, but not symmetrical, not in the sense they are equal mass, but similar masses orbiting each other. So they are orbiting the center of mass here, and you add accretion and dynamical friction. So you are picturing that these two objects are in a fluid environment or even a field profile environment. So they will experience this dynamical friction and accretion, and you can describe them in a Newtonian way. So essentially, you describe the force that are acting in each one of them. And if you try to describe the equation of the center of mass, you get this equation here, right? So this I1 and I2 depends on the dissipative force, essentially. And this is the equation describing the distance, the radial distance between the two objects, right? So what you see, because these objects are have slightly different masses, in the end, the dissipative force acting in one of them is bigger than the dissipative force acting in the other, and this generates an effective force that will act on the center of mass, giving a propulsion to the binary. So essentially, you have the two of them circularizing each other. So because of the dissipative effects, the radius decrease. I'm not putting any GR, so there are no gravitational waves in this scenario up to now. And then what you have is that the radius decreases and the binary goes swimming through the fluid or through the medium that it is. So you can compute the velocity, the maximum velocity that the center of mass can achieve. So this is the maximum velocity for many scenarios, and you can see here that this is in terms of the speed of the light. In some scenarios, it can be 0.1% of the speed of the light, which is roughly 300 kilometers per second. So it's a very high speed. It's bigger than some of escape velocity of some galaxies. And if you compute the time that it takes to reach this maximum speed, it's a reasonable time in the sense that you can observe in some years. So just to show you more clearly the picture is something like that happening. So you have a binary orbiting around the center of mass, and as it goes, you have that the center of mass moves, and then it can reach higher velocities. So this is a video showing how the radial distance evolves, and this is the center of mass dislocating from its initial position. One thing that I want you to notice here is that we started with a circular orbit, so initial condition for a circular orbit if you do not consider any medium, and in the end we are in the with an eccentric orbit, which is interesting because if you remember the effects of gravitational wave, gravitational waves is also a kind of dissipative effect of binaries. But if you remember, gravitational waves, they tend to circularize orbit in the sense that if you start with an eccentric orbit, through the emission of gravitational waves, this orbit will become circular, okay? But what I showed to you is that dissipative effects such as accretion and dynamical friction works in the other direction. So if you take into account gravitational waves and dynamical friction, for instance, you have that the two of them will compete with each other to see how one can affect the eccentricity more. So if you put the two of them together, what you get is something. This is for the gravitational waves. This is for considering only dynamical friction. this is a scenario that you have equal mass to simplify things. And then what you have is something like this. So this depends on the density of the medium, as you may guess. If you have a higher density mediums, easier would be to make the orbit eccentric because the dissipative force would be bigger. And then from this, you see that there is a critical distance in which one effect becomes more important than the other. So for distance smaller than this one, you have that gravitational waves are more effective to change the dynamics of the eccentricity. Okay, so but the thing is, you can see here, okay, for a binary like the GW, the last one, the more massive one, which has 100 solar mass, you may think, oh, this is a very big distance, much bigger than the Schwarzschild radius of this guy. So in the end, the orbit would be circular. But the thing is that from the eccentric, from the dynamical friction dominated part of the scenario, it can kind of earn some eccentricity before reach the stage that the eccentricity starts to decrease. So we integrate the equation here to see how the eccentricity changed. So this is the eccentricity. And we integrate here to see how the eccentricity changed from a starting point. So it changes very nicely up to some point in which it starts to decrease because gravitational waves becomes more effective. And this happens both for when you change the initial value for the eccentricity, or even if you start with a very small eccentricity. But the thing is that in the Lisa band, which is represented by this blue region, you do have some places that you can observe highly eccentric motion, right? So this would be a very interesting thing to search in other improved gravitational wave detectors. So other scenarios to discuss, I put some questions again. The other scenario for depletion, it would be interesting to see these depletions in other scenario to see how it evolves. The one in which the cloud goes away, for instance, in other types of motions like scattering, gravitational wave kick versus environmental kicks, because what I call environmental kicks essentially is the propulsion given to the center of mass. So you know that when particles are orbiting, or when objects are orbiting, the gravitational waves emitted can generate a kick into the binary as well, and this kick can be very violent. So it would be interesting to see how it balances with this environmental kick. So is there a limit for eccentricity gain through accretion and dynamical friction? This is a thing that we recently discovered that some people have looked into that to see if there are some point in which you can saturate some kind of eccentricity. But I think people should look at that more carefully. And finally, how binaries in a bosonic environment would kick. I put this here because sometimes binaries in a scalar field profile can act in a counterintuitive way. For instance, if you throw a rotating black hole into a scalar cloud, it gains like this anti-Magnus kick, right? We all know what is the Magnus effect, which is a ball spinning in the air, so it gains a curve. If you do the same for a black hole, it gains momentum in the other direction, so more or less like this. And then we should be careful in tracing this parallel like I did, saying that it could be a fluid or it could be a bosonic environment and so on. So as a conclusion, there are a lot of things that we can describe with this, with just this action, with just simple things like scalar fields and vector fields. And also there are much more related to many of the seminars that we saw in these past days. For instance, what about alternative theories of gravity? So up to here, I did not discuss any alternative theories of gravity, but it would be interesting to see how this plays out. For instance, how orbit circularizes in the later stage of motion in other theories of gravity. And also black holes are surprisingly simple, but full of surprises as well. To end, I want to just to show you some pictures, because Valencia University was also at my university visiting. So this is the city that I live, and Carolina also lives. So it's a very beautiful city, and we had the opportunity to receive Adria some years ago. I hope him to visit again. I mean, he gave a seminar in Portuguese, which was very nice. Portunhol, we call it. And also he played around with in the beach, trying to simulate binary black holes, I think, with his hand. So thank you very much, and I am available for questions.
Thank you, Caio, for your talk. It was very nice, this last picture of the binary boson stars mimicker.
Yeah. Let me show again.
Okay, well, let me see the...
So just to be clear, I asked permission just before the presentation.
Very nice. Okay, so I have a very general question. So regarding boson stars and bosonic configurations in general, from your expert opinion, what is the most promising scenario to detect the presence of these bosonic degrees of freedom?
The most interesting scenario to detect the presence of bosonic degrees of freedom.
I mean, from gravitational waves, and to detect the presence of these clouds or boson stars, what would be, in your opinion, the most promising scenario?
So I think the modes could be something, but the problem with the modes, the ring now, is that it would also depend on the quantity of the scalar profile that you have, right? For instance, you have the modes from what we have now, but you may also have that this spiral also changed, because I forgot to mention, but this kind of configuration, they emit not only gravitational waves but also scalar waves. So this changes a little bit the spiral phase, in which if you observe for a long time, you could see a signature of something else being hidden there. But I don't know if in this case you could unequivocally say that it is a scalar profile. You know, this thing would be more. The modes would be a more clear distinction, because the frequency of the modes would be there. They would be in the signal. So you can compute the scalar modes. You see.
Okay, and regarding bosonic clouds around neutron stars, for instance, I don't know if both neutron stars typically have any accretion disks. Well, they have things. So, but are there any chances to distinguish between a standard accretion disk from a bosonic cloud?
So for the bosonic cloud, you wouldn't see as clear as the accretion disk, because these clouds, for instance, they can be thought as mimickers for dark matter, for instance, right? So they only interact, at least up to the point that I discussed it here, they only interact with matter by gravitational force, right? So you cannot see them electromagnetically, but they can also change the mass radius curve in a similar way that what Diego mentioned before. I mean, you can have, for instance, higher masses, because you have now the fermion mass, which would be the regular star mass, plus some core profile, which increase the mass. It's not directed to analyze the stability, because, for instance, usually what people say, or at least up to some time ago, was that you could accumulate this bosonic mass in the inner core. Eventually, the star would surpass the Chandrasekhar limit and then would be unstable. but it's not so direct because you have two types of mass. Each of them have their own, if they are separate, they have their own mass radius curve. So the mass radius curve of the entire configuration would change as a whole, and then you would have a new mass limit, for instance. So if you could watch a star with unusual mass, maybe it's because it has something else inside. But this is difficult because, as you can imagine, I mean, it could be this, but it could be something entirely different. So it's not as direct as we expect.
Okay, thank you. So there's a question in the chat, and then Adria also wants to say something, but I think we should first answer the question in the chat. So Marco is asking if you could comment a little more on the reasons why astrophysical black holes have no charge.
Yeah. So there are many reasoning behind this. The first one is that I mean, you have the interstellar plasma. So it's a plasma, and you have charge around that, which could, in a reasonable time scale, neutralize the black hole. The other, you have some quantum mechanisms to create particles around the black hole that could also lead to discharge the black hole, act to discharge the black hole. But I mean, I will leave just these two of them, but usually it's because of that. I mean, essentially you have, if you have some charge, it would pull the opposite sign charge. I mean, the opposite. It would act to neutralize it. I mean, essentially is that. And also, is it possible to have a Fermi boson star? So there is this Fermi boson star, what people call in the literature by Fermi boson star is this kind of configuration I mentioned, which is a neutron star with a bosonic core, right? So if you're talking about that, yes, it's possible. But if you are talking about bosonic fields together with fermionic fields, there are some works on this direction in which they consider fermions combining the certain way that can behave as boson, forming compact configurations. But the two of them together, like a fermionic field interacting with a bosonic field to generate a star, this I'm not so sure that I've seen around. Okay.
Okay, Adrian, go ahead.
Okay, so Caio, you mentioned that there are solitonic boson stars without gravity, right?
Yes.
So I was always puzzled, even in the case of boson stars with gravity. Because with fermion stars you have Fermi pressure, so that stabilizes gravitational collapse and so on. But in the case of boson stars, in principle, there is no known mechanism that should stabilize these objects, yet there exist solutions, right, of the field equation. So, I mean, maybe the mechanisms are known, but I am no expert, and I was always puzzled about how this, if there is any kind of mechanism that maybe is not so well known as Fermi pressure that stabilizes solitonic stars, or it's just, we don't know what happens, but the solutions exist and are there.
So these stars, they do have this self-interaction, but as you mentioned, these are like a bosonic condensate because they are all in the same state in a sense. You put there the n equals 0 and you have agglomeration of bosons. In fact, just after the first work with boson star, there was some people trying to realize the quantum version of it, trying to describe by quantum state. But essentially is that you have the mass that confine your field so that it does not disperse away, right?
Mm-hmm.
And I mean, you have this self-interaction that makes it forms a structure. If you didn't have any self-interaction, you would just disperse the field.
Okay, so this field, for example, so the self-interaction has to be attractive.
Yeah. But I mean, you have the gravitational interaction that attract, right?
Exactly. So in the case of having a gravitational field, do you need a repulsive interaction for the star to stabilize, or there are other stabilizing mechanisms? Because if
yeah. Well, I mean, you have just the self interaction of the star essentially. It's the only thing that you have in addition to the gravitational interaction and the stellar field.
Okay, thanks.
Yeah.
Okay, so we have another question, Fabrizio.
Yes, can you hear me?
Yes, yes.
Yes, so, well, I had like different comments and questions. Like, I really liked your talk. It was very interesting. You talked about many things. And I would really like to thank you like for the questions that you did at some point, like asking if there are ways to put, to obtain more compact objects. And I mean, some of your comments were very interesting. And I think we already talked in chat about them. And I would just to thank you for this. I had one comment about, at some point you talked about Kerr black hole with scalar hair and the fact that they might not be stable, like the work from, well, I don't remember the authors, but there is yeah. So, I mean, as far as I know, this is still like a kind of an open question, right? Like, I mean, these authors, like they did a linear study of some of the solutions from Carlos Herrero and Eugene Radu, and they say that these solutions are unstable because of superradiance. But I think it's still an open topic, right? Because nobody already did nonlinear evolution of these models to assess.
That would be one. I mean, I think you know better than I this kind of subject, but I mean, I have to say that I'm kind of relieved to hear you saying that, because the last time I discussed it about this with Carlos was just when the paper came out. Like, it had like a couple of weeks. And I was pointing to him some of things that I thought to be strange in the paper, and then he was like, "No, I think everything is correct." But and he said the same thing that you said. But
yeah,
it would be interesting to have this solution is stable,
so
and also if the solution is stable. I mean, I think this brings even more things to the table. Because you have a connection between rotating boson star and rotating black holes. I mean, they all belong to the same diagram. It would be also interesting to see the transition between if these solutions are stable, right?
Yeah, I mean, I don't know exactly what's Carlos' opinion about this exactly. I'm not sure 100%, but as far as I know, like at least there might be some region where these models are actually stable. So, I mean, I know that Carlos want to do numerical evolution of this Kerr black hole with scalar hair and Broca hair to assess the stability of them, like to be sure what happened. I mean, I just want to add, like, what you were saying about the connection between the models for boson stars and Kerr black hole, it's true, but I mean, the fact that you have a black hole in the middle might change the things, like talking about the instabilities. Or maybe like this kind of instability, they might be like very long time scale instability so that you will not really see them. I'm just saying this because as you suggested also, like the presence of a neutron star can change the things. So I can also think that the presence of a black hole might change the things. So you know what I mean? Like I think.
I agree with you. I mean I think that would be a very interesting thing to see. I mean, if you prepare something in that direction, I mean, I would be.
Well, we can discuss this because.
No, I would be very, very interested to read it, because I mean it would be very interesting to see how the transition between these unstable modes, and if you put a small black hole in the center of the boson star and see how it grows and what happens to the unstable modes of the boson stars. I mean, that would be a very interesting thing.
Yeah. Like, yeah, I also agree that this will be very interesting, and I know that Carlos want to do this, to look at this. Yeah.
Yeah.
Yeah, this is it. Thank you very much. Anyway.
Thank you.